continue.
Yeah, okay. Okay, so it's 15 past, so let's begin. So welcome everyone for this week's Machine Learning Coffee seminar. So this week we have a really cool talk by Joni Pajarinen, who is an assistant professor in Aalto University on robotics and reinforcement learning. And Joni will be talking to us about Monte Carlo research and curriculum learning. So if you have any questions during the talk, please write them in the chat, or in the end, you can just raise your hand. Okay, so Joni, please go ahead.
Okay, thanks. Like mentioned, I'm an assistant professor and I'm leading the robot learning research group. So what we actually do in our research group is that we develop new reinforcement learning algorithms, and then we have some other topics like multi-agent learning and imitation learning and so on. But then we also work with real robots. So here you can see some pictures on the bottom of the screen. So there we have, for example, two robots collecting information about the scrap heap, and another picture where the robot is trying to disentangle, so physical disentangling of objects. And then we have also this research on reinforcement learning, where we really develop new methods and publish them in machine learning venues. But today I will talk about reinforcement learning and not so much about robotics. So the talk is divided into two pieces. So the first part is I will talk about Monte Carlo tree research. So Monte Carlo tree research is a way of planning actions or deciding on what is the best action to do if you have a simulator or a model of the environment that you can use for planning. And here are illustrations of the tree. So these are, we don't use real trees, but these are just for illustration purposes. And then the second topic is curriculum reinforcement learning. And well, curriculum learning just means that you start from an easy task and then go towards a harder task. And this makes the learning easier. So this is also what humans often do, that they start with something easy and then progress to harder challenges. Okay, now before we discuss the details of these approaches, let's get to the basics of reinforcement learning quickly first. So here we have a picture from Sutton and Bartos' well-known reinforcement learning and introduction book. And we have an agent in the environment. And here's an example, like a robot on Mars. And the agent performs an action. This could be, for example, move or pick up an object or whatever it is. It could be also some kind of like wireless network, the system or anything. This is a very general framework. And when the agent has performed the action, the environment changes. So for example, if the agent pushes a box, then the location of the box changes. And the agent gets, in the next time step, the agent gets information about the change state. And in addition to the state, the agent gets at each time step information about the reward. And the reward is something that you specify to show the agent what you actually want to be accomplished. So for example, the agent could get a reward for picking up a box if the task is to pick up a box. And typically what we then try to optimize is a reward over several time steps. And here we have an expectation over the rewards, because the system can be stochastic or the agent can have a stochastic policy. So we are thinking about the average reward over several time steps that we want to optimize. And the methods that people will usually use for this is, for example, optimal control or reinforcement learning, which we will talk more today about. Okay. And now there are a couple of different challenges in reinforcement learning, and different research focus on different points of view. So today we will talk about mainly about how to choose actions that actually allow the agent to behave optimally. And there are methods for which there are actually proofs that in the end you will end up with an optimal solution if you have enough data. And the second point we will discuss today is how to choose the learning environments that actually allow the agent to learn optimal behavior. So we will choose environments in a sequence that make the agent better. And then there are other topics like if you want to learn dynamics models or how to represent the policy and dynamics and so on. But we will not discuss those today. Now, Monte Carlo tree search has been used in several different application domains. And the first one here, this Go game, is maybe the most well-known. So this is a board game where you have 19 times 19 different possible locations where you put a stone. And then if you think about this as a kind of like a search problem, so for each stone you put, you have these 361 choices, and then for the next stone there are 360 choices. And this means that the tree grows very big and very fast. And the classical methods for Go and chess and so on have been based on this kind of like tree search and min-max techniques and large databases of expert moves. And what Monte Carlo tree search brings to this, it's kind of focused the search into very promising directions, and it has yielded very good performance, for example, in this Go game, beating the world champion. So this is like maybe the most well-known example of Monte Carlo tree search. But it can be also used in many different application areas, also in robotics. For example, here on the right top side, there's an image of two robots collecting information about fruits. And then on the left bottom, there's a robot trying to manipulate objects. One thing that we should note here is that the decision-making typically that you do with Monte Carlo tree search is limited to discrete actions. So you do high-level decision-making. And we will also assume this today. There's some work that extends it to continuous actions, but we will not discuss it today. So this is kind of like the most common way of using Monte Carlo tree search, of having discrete actions and discrete states. Now let's get into a little bit more details. So you can divide Monte Carlo tree search into 4 different phases. And this Monte Carlo tree search planning, when you have an agent in the environment, it does this planning typically in each time step. And the planning consists of growing this tree and then choosing the action at the root node that seems most promising. And our contribution is in this back propagation phase that I will talk about in a couple of slides again, a little bit more in detail. But okay, let's talk about how Monte Carlo tree search works. So we start in this root node. If you look at this selection part of the figure, I hope you can see this. And the root node is at the top. And then you select one of the actions. So it's this red edge that was selected in this case. And this is done using a bandit. And the bandits have some convergence proofs that tell how to use all the data that has been gathered before to do the choosing of the action. And then you move to the next node, and then in this case, you sample from the system a new state that depends on the action you executed. And then you move to a new node again, that's the second red edge. And then finally you use another bandit to choose a new action and so on, until you arrive at the leaf node at the bottom of the tree. And then the tree is expanded, and then we go to the third phase of simulation. So typically what you do is you execute some random or heuristic policy there at the leaf node to collect values. Or often also nowadays what people do is they use reinforcement learning to compute some kind of estimates for the leaf nodes, so they don't need to do these rollouts at the leaf nodes. And then these estimated values are back propagated along the tree to the root node along these red edges on the right side of the image. And the back propagation is the phase where we did our contribution in this work. To give a kind of like a little bit more understanding of how or what is the kind of like the power of Monte Carlo tree research in general, I will now discuss the selection phase a little bit. So at each node where you make a decision, so you choose an action, you typically use an upper confidence bound, for example. This is like one bandit. So the bandit is a keyword you can Google, and upper confidence bound is another keyword you can Google. So use an upper confidence bound to estimate what action you would like to do. So the bandit trades off between exploration and exploitation. Exploitation means that you would just take the action that looks the best at the moment based on your finite number of samples. And exploration means that you would also choose other actions to try out different ways of behavior for the agent. And you want to have something that balances between these two so that you end up with a solution that actually gives you optimal behavior, but with a small number of samples. So this is a very general problem in reinforcement in general. How to use the data most efficiently. And this is kind of like the power of Monte Carlo tree research, that it can direct the search into regions which seem promising, but without compromising the end result. Now, okay, now to the back propagation phase. So you can see this is again this search tree where we have the red edges. And typically what people do in Monte Carlo tree search is they just take the average over all the samples in a node to estimate the value of the node. And another possibility is to use the maximum operator, so take the action with the highest value. For this, however, there is no convergence proof, at least to my knowledge. So, so these are kind of like two typical choices. There are a lot of other ones also, but these are maybe the two most common ones. Now, if we want to then illustrate what happens to the tree when you use these two approaches. So when you use the average approach, the tree grows very wide, but it doesn't plan very far into the future. On the other hand, if you use this maximum operator, then the tree is narrow, but you plan also far into the future. And what we would like to have is something in between these. So we want to have something where we can, first of all, we want to prove that we converge to the optimal solution, which can't be done for the max operator, but we still want to have like a policy that looks far into the future so that we can do optimal decision making. And how do we then do it? So we propose the power mean operator. So this is a rather simple modification to the average operator. We have an additional hyperparameter p here. So we take the average values to the power of p, and then take the p root of the whole thing. But basically the main properties of this average operator are that for p is 1, it corresponds to the average operator, so it's just the mean. But when the p goes towards infinity, it corresponds to the maximum operator. So with this, we can have properties of both operators and choose a p-value that fits to the problem at hand. And this is joint work with Tuan Dam and then Pascal Kling, Carlo De Ramo, and Jan Peters from TU Darmstadt. So this is basically the main contribution in this work. And for this power mean operator, we derived convergence proofs. So I won't go into the proofs today, that would take a lot of time. But basically we can prove that for any p, any finite p, the algorithm converges to the optimal solution. And this is maybe a little bit surprising that even if you have a very, very large p, it still converges to the optimal solution. But it just means that if you have a lot of data, then this applies, and we also were able to compute the bias of the estimated expected payoff. So this means just like how how incorrect your estimate of the rewards can be, after a certain number of time steps. So n is the number of time steps here. Okay, and here you can also see an illustration of the beautiful tree. So it's not this kind of like wide tree, wide short tree, or long narrow tree, but it's this kind of like more symmetric tree that looks much nicer here. Now this is basically the end of this Monte Carlo tree search part. So if anyone has questions, I can ask. I can also discuss Monte Carlo tree search, or we can take them then at the end of the presentation. Okay, yeah, let's go on. Now let's go to something a little bit different. So the Monte Carlo tree search was more about planning actions, but curriculum reinforcement learning is having an agent go around in the environment and then learn from the experiences. And what we propose is self-paced curriculum reinforcement learning as a new way of doing curriculum reinforcement learning. And basically the idea, just to remind you, in curriculum learning is to start from an easy task and then progress to a harder task. And this makes or should ideally make the learning easier, so that you don't need to immediately start from the hard task. And in our work, we wanted to have a method that is, first of all, principled, does it in a principled way. So this is something that was lacking in the literature. And the second thing is that we wanted to have an approach that can automatically decide what is easy and what is hard, and then automatically converge from an easy to a hard task. And this is joint work with Pascal Klink and also Hani Abdul Samad Boris Belousov, Carlo de Rama, and Jan Peters from TU Darmstadt. And now let's introduce an example task that we will use as an example in this presentation. So I hope you can see, so there's a ball. So it's this tiny red dot. It's far in the distance. And then we have a robot arm. So the robot arm can go around and try to catch the ball with a net. And then the robot arm has some limitations how the joints of the arm move. So it's not just moving a point around, but you really need to think about how the robot arm can move so that it catches the ball. And of course, if you now throw the ball towards the robot, then it's obvious that it's easier for the robot to catch it if you throw it directly into the net than if you throw it like far away from the net. And now the idea is that we would then have an algorithm that would automatically find out what is easy and what is hard, and then make the task progressively harder. And here you see some examples of the robot arm. And as you can see, when the robot or the ball gets closer to the robot, then it becomes easier for the robot to catch the ball. And here again on the top of this slide, we have the same state action loop that I showed earlier in the beginning. It's just defined in a little bit different way. So on the left-hand side, we have the reinforcement learning agent. It has a policy pi, and then omega are the variables of the policy of the whole agent. So basically the policy, and then we have the value function v. And the policy specifies what action to take when you are in a specific state. And the value function specifies what is the value you expect to get with a certain policy when you start from a state S. And then we have again this agent that performs actions, the environment changes, and then the agent gets a reward and state feedback. And the goal is to maximize this expectation of the value function. So this is the same thing here, the value function, as summing the rewards into the future. So there's no difference yet compared to that. And we want to find the parameters of the policy, so the parameters omega, that maximize this value. So that is the goal here. But this is a very hard optimization problem if this could just this ball catching for regular reinforcement learning algorithms. And here we show how we can use curriculum reinforcement learning to improve the learning. And the idea is to choose the task in a very nice way, such that, well, like said, that the agent will start from easy tasks and go to harder ones, but have like constant learning all the time. And how we do it is we say that we have now a context, and the context is basically just some parameters of the environment. And then we say we have a context distribution. So we have a desired context distribution. In this case, it could be, for example, a Gaussian distribution that's has a pretty high variance. So that this means that the human could, for example, throw the ball either close to the robot or far from the robot. So this is the desired context distribution that we want to have in the end. But then we will start from easier context distributions, and we let the algorithm choose the context distribution to start from and to progress from towards the hard final distribution. And you can see this with this green color. I hope you see this context variable C. So we put it as part of everything here. So the policy depends on the context and the value, because basically the context defines the environment. How does the environment look like? And in this specific case of ball throwing, the context variable just specifies at what position the ball should pass the robot arm. And if the ball passes very close to the robot arm, then it's easier for the robot arm to catch the ball and to learn how to move towards the ball. Okay, so this is the basic idea. Now, how do we then do the optimization so that we can end up with the kind of solution that we want to have? So there we, oh wait, I think I can maybe, okay, yeah, this looks better now. So in this case, let's start looking at this slide from the top. So on the top, we have this optimization objective where we maximize the value function. And then we have a KL divergence. So between the current context distribution P and the desired context distribution mu. And we want to minimize the distance between the current context distribution and the desired context distribution, but at the same time, we want to maximize the value that the policy gets in the current context distribution. And this argmax here is just that just chooses basically the parameters of the context distribution in a way that maximizes this whole objective. Then we also have this KL divergence constraint between the previous context distribution and the current one. So this is just a trick that is often used in reinforcement learning. Because we have a finite number of samples, we want to keep the learning stable. So then we often add this, you can add these kind of like constraints so that the learning does not jump around too much. And okay, so this is like one part of the optimization we then do. Then the second part is then below that, the one that now appeared on the slide. Here we maximize the parameters of the agent, so the policy parameters and the value function parameters in such a way that that we maximize the value function for the current context distribution. Yeah. So okay, one thing I need to mention is that we don't necessarily change the value function parameters, but the parameters of the policy that influence then the value function we compute. So yeah. Okay, and these are, now we have like two maximization problems, and we can interleave them and execute them after each other. And these optimization problems are connected by the desire to maximize the expectation over the value function when starting from the initial state as 0. Yeah. Okay, so but what you really need to just remember from this is not all these details, but just that we have two things. So we maximize the context distribution so that we get closer to the desired context distribution, but still maximize the expected reward. And then we also maximize the policy parameters so that we maximize the expected reward for the current context distribution. So these are the things just that you might want to remember. Now, then we have this nice animation here on the left bottom side. And here you can see the contour shows the value function that you can get basically. And then these dotted lines show the probability distribution. So the red dotted line shows the desired context distribution, and the black dotted line shows the current context distribution. And when this alpha parameter starts from 0, it gets to a very easy context distribution. But then when we grow the alpha, it then transitions into the red context distribution, giving us the desired task in the end. And how this all then, what is the end result in this is that we actually get the learning procedure where we start from an easy task, which we automatically find, and then we automatically change the task distribution until we get to the final task distribution. And we have kind of like the learning speed looks constant, so you learn all the time more, but then you end up in the final challenging distribution. Now here's an illustration of from our experiments. So here we have an AND task. So AND is something that is very commonly used in reinforcement learning. So you have to control this. I don't know why it's called an AND. It has only 4 legs, but you have to control this 4-legged AND, and you have to control the joints of the AND. So you have to learn locomotion. You have to learn how to move the AND. So it's not just a point going around. You have to really control the legs. And in this task, you have to go through this narrow gate on the other side of the wall. And the reward is such that when you get closer to the bottom, you get higher rewards. And this makes it hard for optimizing the behavior of the AND. So if a standard reinforcement learning algorithm, it will get stuck at the wall. But then you can make the task easier. So you can move the gate and you can make it bigger or smaller. So basically we have 2 parameters, this position of the gate and then how wide the gate is. And these are then the context variables in our case. So in the kind of like in the beginning, the AND would then, well, the algorithm chooses the initial distribution, but it would probably start from this kind of like wide gates and then into finally end up in these narrow gates that are further away from the agent. So it's harder to find a good solution for that. And okay, here are then some animations. So now in the top right, you can see the kind of like the standard reinforcement learning. It doesn't really find any solution. And each AND here, so this is not a multi-agent system, but these are just different instances. So you should see kind of like the distribution of how the optimization goes. And then you have a random curriculum. It works already much better than the default learning. But the ants still don't necessarily all get through the gate. And then there's another curriculum learning approach, and another one, and our own approach. And in the end, I don't know why the video is so stuck now a little bit, but okay, anyway, so our approach then gets through the go gate in a better way here. Okay. Anyway, yeah. So in the end, we could summarize the whole talk in a couple of ways. So first of all, we have Monte Carlo tree search, which gives you very nice convergence proofs, and it works also in practice very well in these decision-making problems, for example, in gameplay, or if you make high-level decision-making in robotics and many other tasks. And then we had the curriculum reinforcement learning approach, which starts from an easy environment and then moves on to harder environments. And then we also have at our robot lab, we have a Boston Dynamics spot robot with a robot arm. And so if someone wants to collaborate on the spot robot, they can contact me for that. So the robot can also climb stairs and pick up objects and so on. So with the arm. Yeah, thanks. Yeah, I'm ready for questions now.
Okay, thanks a lot for the really interesting talk. Yeah, any questions? So if you have any questions, you can raise your hand or maybe write in the chat. Okay, so we have a question from Anna. Anna, would you like to ask it?
Okay, hello. So for this reinforcement learning, you need a lot of data, right? A lot, like much more than for other algorithms, right?
Yeah. So the problem you could describe is that so in supervised learning, you know exactly what you want to have. In reinforcement learning, you need to kind of like find it out. So it takes more data, and that's kind of like one of the main research questions at the moment. So how to do reinforcement with as little data as possible.
So do you think now in modern world we have those areas where you have that much data? Because data are the problem in the real life tasks.
Yeah, so well, it depends a lot on kind of like the problems you think about. So for example, in this gameplay, it's already kind of like the leading approach. So but of course, if you think about like controlling robots, then I would say it's you can use reinforcement learning, but often you also need to combine it with other methods. So for example, if you want to use, well, it depends a little bit like what methods we are talking about, but if you, for example, use Monte Carlo tree search, you could use it for high-level decision making. So let's say you want to pick up objects, then the Monte Carlo tree search could tell you, okay, pick this object up and move it in a specific place. And then you could have like a low-level controller that performs the movement. But I think reinforcement learning at the moment can be used in practice, but you just need to split the problems in parts that can be then solved reasonably. And of course, the research is also going, I mean, the kind of like the final end goal in many people's minds is this kind of like system that just takes images of the environment. So robot goes around, takes images, and then you directly learn how to move the robot arms and legs and so on from these images. But of course, this is a little bit still not possible at the moment in complex situations, but that is one of the research things that is going on at the moment.
Thank you.
Okay, Sam seems to have a question.
Hi. Yes, so thanks for the talk. Actually, I watched this at NeurIPS posture as well. So it's good to see it being presented again here. So one thing I was wondering about this was how the self-paced algorithm can be extended to discrete distributions over tasks. So for instance, in this ball catching thing, like that task distribution is like continuous, right? Like you can shift the gates by like a little bit and then the task is sort of marginally harder. But then what happens if I don't know, like I'm doing a lot of work in this environment right now where like you might learn to go to an object and then you have to learn to like pick up an object, right? And like there are only those two tasks which are available. So I'm wondering if you've looked into it, extending it in this direction.
Yeah, we have a version of the algorithm that works also in the discrete case. I'm not sure how good. I think the results are okay, but I think then if you well, it depends a little bit on the task whether it makes sense then to use this self-paced learning or not. And so, but maybe the best would be to actually discuss this with Pascal. So we have tried it out, but we have not focused very much on the discrete case because I think the continuous case looks a little bit more promising, at least at the moment. So there are no big problems, I would say, in the discrete case, but maybe the difference to comparison methods is not as big as with the continuous case.
Right. Okay.
And okay, actually we have also some, well, okay, no, wait, that's only, yeah, we have also some new work that we are now submitting that also uses the discrete case, but it's a little bit, yeah, different. Maybe I can talk about it later when it's published or yeah.
Okay, so this is not the JMLR reference, but this is something else.
No, this is something that has not been presented anywhere. So it's about extending the distributions in a very general way that we can use for the context distributions. But let's see if we put it on archive, then I will try to put it on our webpage at least, and or send to some people if they are interested.
Yeah, that'd be interesting to hear about.
Okay, so we still have plenty of time for discussion if there's other questions. So maybe while the audience is thinking, I have questions. So in the last example, you had the gate that was moving left or right. And it seemed that you had to define that there is a gate and that it can move like this. Do you think it would be possible to somehow let the system learn what kind of augmentations it wants to do? For example, maybe the system can learn that, okay, you should rotate the gate instead of moving it along a predefined axis. Do you think this kind of fully automatic system could work?
Yeah, that's yeah. We have not presented any work on this, but yeah, this would be an interesting direction. And what I also personally think is that, for example, if you do model learning and then learn kind of like low-dimensional characteristics of the system that can kind of like where you can control the system very easily. You could use that also as part of this self-paced learning, so that you would then, for example, automatically learn the features of the environment that would be interesting for you. But we have not done much in that direction yet, but are maybe planning to do that. Yeah. So, but yeah, definitely, I think this is an interesting research question and direction. So how to learn these kind of like features or context variables in a way that you can modify the environment in interesting ways.
Okay, thanks. So I'm not seeing any further questions. So in that case, I will thank the speaker and thank the audience for your attention. This was really interesting. And we will then meet next week when we'll have a talk by Nuutti Steen. Okay, so have a good day, everyone.
Thanks, everyone.
Thank you.
Goodbye.
Kiitos Joni. Mieletön kyllä esitys. Todella mielenkiintoinen aihe ja sulla oli ihan mielettömät nämä illustraatiot siinä. Olitteko te itse keksinyt tämän puuesimerkin vai onko tämä joku niin kuin yleinen?
Ei, kun toi puu on mun keksimä ja sitten noin tuosta self-paced ja animaatit, ne on kaikki mun jatko-opiskelijan kehittelemiä.
Joo.
Tuo puu